Hello, we are Group 3 in Section A6, and this is our presentation about the IC Engine Lab. We are Josh, Nate, Jasmine, and Nick. Here we paste in an honor code outlining our honor. Next slide. Um, the basic purpose of this lab is to characterize a coworker's engine, internal combustion engine, and mathematically describe the engine components, the torque, the RPM, and the inertia, as well as calibrate the sensors that we're going to be using here. Our data was collected with a force transducer that's mounted on the motor, as well as the angular position was collected from the engine position. This, along with time, allows us to take in the torque, angular position, velocity, acceleration, etc. The force transducer was calibrated from adding known weights to the motor and deriving the torque equations. After the data was collected, we needed to process it. The angular displacement needed to be changed into a monotonically increasing value, and the angular displacement values were also averaged to get average torque, time, and angle for processing later on. Now we will discuss the details of the lab.
So first for the results, I want to discuss the torque calibration. This step allowed the raw data to be converted from volts to Newton meters. After conducting the linear regression that allowed us to obtain the calibration equation and respective confidence intervals for the offset, we analyzed the torque time data to ensure the calibration made sense. Knowing and expecting zero torque at the beginning of the dataset, the error can be directly observed. The value of negative 0.02242 Newton meters means the calibration overshot the expected value, but since it is within the confidence bounds, the calibration can be said to have been successful. On this slide, the point used in deeming the calibration successful is shown. Following that discussion, I want to discuss the two primary equations that comprise the mathematical model of the IC engine. Everything stems from the energy balance presented in the first equation, but using either a steady state or transient condition, different simplifications can be made. At steady state, the angular velocities at all angles will be the same, making the left-hand side equal to 0. When accelerating from rest, the angular velocity of the flywheel at an arbitrary point can be set to 0. In both cases, there's no engine head, so there's no air pressure, and thus no work done from that. It is important to note that the work done due to the piston can be assumed to be negligible, turning this into a system with two equations and two unknowns, which we evidently solve later on. The first unknown variable to determine in this experiment is the work due to friction. Knowing that it's equal in magnitude to the work done by the motor, the three steady state torque versus angle graphs were integrated, and then all you have to do is multiply that work by -1. To determine the torque due to friction, the work was then divided by the angular displacement. The results demonstrated an interesting trend between RPM and torque, which then raised the question of whether this trend made sense.
During the lab, we made the assumption that the torque due to friction is constant no matter the RPM. As you can see in our data, this is not true, as in the plot on our right, in the same amount of radians, more work is done the higher RPM you go. Moving on to the moment of inertia, we have our theoretical value and our experimental value. Our theoretical value was easily calculable by the equation given, and we had a mass and a radius. There were 4 flywheels, so we got a moment of inertia of 0.00994. In order to obtain it in the experiment, using the equations before, we can simplify the bottom equation into, next slide, the equation for our moment of inertia of the flywheel. We determine the work due to the motor through the numerical integration of the graph on our left. We have our torque due to friction from the past experiment, and we know the theta change, the degree of change of our angle. We cannot start that integration until the wheel starts to rotate. So on our right plot, we cannot start until approximately 2 seconds in. our omega flyby is taken from the change of theta at the end over the change of time to give us our omega value. Doing this results in a experimental value of 0.009. That is close to our theoretical value and is off due to the assumption that the work due to piston is negligible and the work due to friction is constant.
Now, continuing this discussion, we found that removing the flywheels actually results in an increased engine acceleration. Basically, looking at plot 42 of the crankshaft angles versus time between the relationship of flywheels and non-flywheel experiments, we see that removing the flywheel results in a steeper slope or velocity of the engine. And so this higher velocity translates to a higher acceleration when the flywheel is removed. We also see that for the intake and power stroke of our crankshaft angle, we see a 0 degree mark, and during compression and exhaust, we see it at 180 degrees. Now, during the intake and exhaust of this engine 4-stroke cycle, the valves are open, and during compression and power, the valves are closed.
So concluding all of this, a greater RPM gives greater torque due to the increased loading from the frictional forces. This also gives increased work per radian and increased work overall. We also know that removing the flywheels increases the acceleration of the engine, and we found that the calculated values for the voltage offset and moment of inertia were relatively close to our theoretical values. In the next slide, we've got our references to the laboratory manual and the PowerPoints, and we have pasted our MATLAB code for reference in the very end. Thank you for watching our presentation.